Hello everyone, my name is Ri Liu. I'm a PhD student from Inner Mongolia University of China. I'm also an exchange PhD student at the National University of Singapore. I will make a presentation about our paper on TTS. This is a joint work of Inner Mongolia University of China, National University of Singapore, University of Bremen in Germany, and the Singapore University of Technology and Design. The title of the paper is Teacher-Student Training for Robust Tacotron-based TTS. This is just a quick outline of what I'm going to talk about. We will now come to the first section. A text-to-speech system converts text into human-like speech. With the advent of deep learning, end-to-end TTS has shown many advantages over the conventional TTS techniques. For example, Tacotron-based approaches have shown to achieve remarkable performance. In these techniques, the key idea is to integrate the conventional TTS pipeline into a unified network and learn the mapping directly from the text-to-speech pair. However, neural end-to-end TTS is still far from perfect. Most of the time, this suffers from the exposure bias problem in the autoregressive model that is used by the decoder module. This problem results a mismatch issue, especially for out-of-domain test data, that leads to unpredictable outcomes, such as skipping, repeating words, incomplete sentences, and inappropriate proceed phrase breaks. In this paper, we propose a novel teacher-student training scheme for neural end-to-end TTS framework that performs remarkably well for out-of-domain inference. Next, I would like to turn to some related works. Tacotron model based on an encoder-decoder architecture with attention mechanism. Furthermore, together with a neural encoder, natural-sounding human-like speech can be generated. The encoder consists of two components, the CNN-based module that has 3 convolution layers, and the LSTM-based module that has a bidirectional LSTM layer. The decoder consists of 4 components, a 2-layer prenet, 2 LSTM layers, a linear projection layer, and a 5 convolution layer postnet. The decoder is a studied autoregressive recurrent neural network that generates the Mears spectrogram features and stop tokens frame by frame. However, Tacotron-based TTS is still far from perfect. It suffers from the exposure bias problem in the autoregressive based decoder module. Specifically, in training stage, the decoder generates a frame using its previous frames of natural speech as input that is called teacher forcing mode. However, in inference stage, the decoder predicts a frame using its previously predicted frames as input. That is also called free-running mode. There exists a mismatch between the natural speech frames and the predicted frames, especially for out-of-domain test data. That leads to skipping, repeating words, incomplete sentences, and inappropriate proceed phrase breaks. Recently, some techniques were proposed to improve out-of-domain performance, like schedule sampling, various attention mechanism, and the GAN-based method. All the methods mentioned have made great contributions. While different from the above works, in this paper, we propose a teacher-student training scheme for Tacotron-based TTS framework that performs remarkably well for out-of-domain inference. We call it Tacotron-2 KD. The main contributions of this paper are summarized as follows. We propose a compact method for end-to-end TTS model. We propose a teacher-student training scheme for Tacotron-based TTS model. The proposed framework works remarkably well for out-of-domain test data, both in Chinese and English. To our best knowledge, this is the first implementation of teacher-student training scheme for Tacotron-based TTS framework. This session looks at the framework of our proposed method. In this scheme, a teacher model learns the text-speech mapping from training data in teacher-focusing mode, while a student model learns from both the probability distribution of the teacher model and the same training data for teacher model in free-running mode. The process of student learning from teacher model is called knowledge distillation, and its learning objective is called distillation loss. While both the teacher model and the student model have identical network architecture as the Tacotron-based baseline, they adopt different decoding mode as shown in this figure. Next, we will discuss in detail the teacher model, student model, and the teacher-student training scheme. In practice, we first train a studied Tacotron-2 teacher model for an end-to-end TTS system under the teacher-focusing mode. This is regarded as the teacher model. As the teacher model learns under the teacher-focusing mode, it's accepted to represent the true distribution of the natural speech data. As can be seen in this figure, we define Y objective function for the teacher model, the feature loss. Next, we then train another Tacotron-2 student model under the free running mode. As the student model is trained under the free running mode by using the predicted speech frames as the input of the decoder, it's accepted to accustom itself to the runtime inference condition. The student model is trained by learning from both ground truth sequence and the hidden states of the teacher model at the same time. By learning from the hidden states of the teacher model while knowledge distillation, the student model learns the true distribution of the natural speech data effectively. We devise two objective functions for the student model, one for the feature loss, that is the same as in the teacher model, and another for the knowledge distillation or distillation loss. The student model is trained with a combination of two loss functions under the free running mode. With the instruction of teacher model, end-to-end TTS model can gain significant improvements and has a more stable performance when dealing with challenging sequences. I'd now like to move on to experiment part. We conduct some experiments to evaluate our proposed method for Mandarin and English language. To verify the effectiveness of knowledge distillation, denoted as Tacotron-2 we choose two baseline frameworks. The first one is Tacotron-2 with schedule sampling, denoted as Tacotron-2SS. The second one is Tacotron-2 with free running mode, denoted as Tacotron-2FR. In all experiments, we use Graphlin algorithm for waveform generation for rapid turnaround. We first evaluate the sound quality of the synthesized speech with mean opinion score among Tacotron-2SS and the proposed Tacotron-2 that is reported in Table 1. It's observed that the proposed Tacotron-2 clearly outperforms the baseline Tacotron-2SS for both English and Chinese data. Because Tacotron-2SS is better than Tacotron-2FR, we only chose Tacotron-2SS to conduct pre-first experiment and the WER experiment. The AB pre-first test is reported in Figure 1 and 2 to compare Tacotron-2 and Tacotron-2SS in terms of voice quality. It's observed that Tacotron-2 outperforms Tacotron-2SS consistently for both English and Chinese data. We further conduct experiments to evaluate the robustness of synthesis speech for Tacotron-2SS and the proposed Tacotron-2 KD, as reported in Table 2. We measure the robustness by word error rate that reports the sum of repeats and skips over the total number of characters in the listening test. It shows that Tacotron-2 KD effectively reduces the errors over the Tacotron-2 SS baseline. Finally, we conclude this paper. We have studied a training scheme for Tacotron-2 to perform high-quality speech synthesis for out-of-domain text that overcomes the exposure bias problem. We implement the teacher-student training scheme through a knowledge distillation objective function. The proposed Tacotron-2 KD framework consistently outperforms the baseline systems in both English and Mandarin in terms of naturalness and robustness. Thank you all very much for taking the time to listen to this presentation. If interested, please check our demo page to the synthesis of speech samples. Thank you for your attention.